Morning, folks. The subject of today's video is how to troubleshoot an amplifier that's stuck in protection. And this tends to fall under two broad scenarios. The first one is the protection circuit is doing its job and there's something wrong in the amplifier. And the other scenario is that there's something wrong with the protection circuit and there may or may not be anything wrong with the amplifier. We need to determine that in order to know where to focus our attention. So this is going to necessitate a discussion of the protection circuit, what it is, why it's there, and why it does what it does. While there are variations, the vast majority of protection circuits and amplifiers consist of circuitry that controls a relay, and the contacts of this relay sit between the output stage of the amplifier and the speaker terminals on the back of the amplifier. The circuit will look at the amplifier, and if everything is copacetic, the amplifier is working okay, the relay will close and it'll connect the output stage of the amplifier to the speaker terminals, and now you can use the amp. If there's any excessive DC voltages, the relay contacts will not close. In addition, there's circuitry in most protection circuits that delay the closing of the relay a few seconds, and this allows the amplifier to stabilize after you put power to it. And this helps mitigate any pops or transients that might be range anywhere from annoying to speaker damaging. And also, when the relay contacts open up when you turn the amplifier off, that also prevents any noises. So what should become obvious at this point is that the protection circuit is not actually there to protect the amplifier, but to protect the speakers connected to the amplifier, because in all direct coupled amplifiers, you could have a malfunction that will dump huge amounts of DC voltage onto the speaker terminals, and this DC voltage can damage your woofers. If there's enough of it, it can burn or open the voice coil in your woofer. Now, it shouldn't affect anything else because the capacitors in the crossover network will block any DC and prevent it from smoking a tweeter or even a mid-range. And this is why you don't see protection circuits in capacitor coupled amplifiers. These are amplifiers that have a large coupling capacitor between the output stage and speaker terminal. And by their inherent design, they can't dump scads of DC out. The coupling capacitor will simply block that DC from passing. Let's take a look at some basic protection circuits, and I'll break down each portion of it so you can see how they work. So these are basically the three blocks that we deal with when we're looking at a conventional protection circuit. And of course we have the relay drive, which runs the relay, turns it on or off. We have startup delay and the voltage detector, which looks at each channel of the amplifier to see if there's excessive DC voltage. So what I've done is I printed out three different schematics from items I've worked on in the past, and we're going to go through each block and I'll show you what they do, and then we'll talk about how you troubleshoot a problem like this. So the first one up is the Sansui Au717. For whatever reason, I've probably seen more of these than any other single amplifier. But anyway, this is the schematic representation of our relay. These are the contacts, and this connects the output stage, and these go, they don't show up, but these go to the speaker terminals on the back. So our relay is right here, and this is our relay drive transistor. You'll notice that every one of these relays and all these schematics will have a diode that goes across it. This is called the flyback diode, and its function is to protect the transistor from the large transient that will come when you turn the relay off and the magnetic field around it collapses. If you know about how coils and inductors work, if you've watched my series, you'll know that this is a crucial diode, because without it, first time this turns off, there's a good possibility this transistor will be destroyed. So this is our relay drive, and the way this works is When the voltage reaches a certain point here, about 0.6 volts, the transistor will become forward biased and will pull in the relay contacts and close these contacts here. And that will give you continuity from the output stage to the speaker terminals. Our startup delay is almost always what they call an RC network, consisting of a resistor and a capacitor. In this case, there's a 330 microfarad capacitor and a 39 k ohm resistor. And the way it works is, as this capacitor charges up through this resistor and reaches a certain point, I'm not sure what the value of this zener is, it will turn on this transistor and pull the relay in. So we have our relay drive here, and a relay of course. We have our startup delay, and then we have our voltage detector. Now, up at the top of the schematic here, you'll see two resistors, R39 and R40. Sansui has a convention that they will only give you the values of one channel. So we see this is 22K, and it doesn't say, but this is also 22K. I believe their feeling is that if you put all the values and the voltages and everything all on here, the schematic gets too busy to make sense of. And I do understand that. So what they do is, on the left or right channel, the left channel will have the values, the right channel won't have the values, but will have the expected voltages. So that's why we only see 22K here. But in the vast majority of cases, these are all going to be the same. These just go to the outputs and provide isolation. Because if you just simply tie these two together there, the output stage would blow up. So we need to have some way to isolate them from the voltage detector. So this goes down through a diode to here. This goes down through a diode to here. And you have a diode and a what they call bias diode. This is basically two diodes in tandem. And if we get voltage high enough to forward bias this transistor, it will forward bias this transistor and discharge that capacitor, turn off our relay drive, and open up the relay. Now, this is how basically all of them work. This is our protection circuit. This over here, this interesting looking configuration, is known as a monostable multivibrator. It's not part of the protection circuit. This is simply make the power light flash on and off until the amplifier comes out of protection. That's the whole function of that. So it doesn't really come into play here. This is our protection circuit. So that's how they do it on the Sansui Au717. Moving right along, this is a Mitsubishi I recently worked on. This particular amplifier had a problem in the protect. And what it turned out to be was one of these diodes was physically cracked in half. This is basically the power supply that runs the protection circuit, and that's where our problem was in this particular case. We had AC volts coming through here. We had a resistor here, 220 ohm, half watt. I believe this is Mitsubishi's symbol for a fusible resistor. But going back to how this works, we have our relays, and it's kind of interesting because Mitsubishi does things a little differently here. They use two relays instead of one, and the relay contacts are shown off to the side here, but the relay coils are shown here. So it's just a little different schematic representation of the same thing. You'll notice we have our flyback diodes. These are tied in common because both relays are going to either close or open at the same time. So this is our relay drive transistor. And this comes from this transistor here. Let's see, where are we at? And this is our time delay circuit, and I'll go through a little more on how this is all working, but here's our capacitor, and here are two resistors. Now they use a lower value capacitor, but a higher value of resistor. End result's pretty much the same thing. It takes longer to charge through these resistors, even though it's a smaller value of capacitance. And anyone who watched the video might have heard me remark that, wow, this thing came out of protection really quickly. And before I returned it to the owner, I pulled that capacitor, and sure enough, it was bad. I replaced it, and then it was the requisite 4 or 5 second delay. So what we have here is, once the time delay period is elapsed and this is charged up, it will forward bias Q301, which in turn will come over here and forward bias Q303, which then in turn goes over to Q304 and fires that up. Now our voltage detector, those guys are here. Both 33K are 134 and 135. And they go here, and if we get voltage here, it's going to forward bias this transistor, and it is going to kill our voltage here and open up the relays. Last one is a Marantz 2265B. So here's our relays. Here's our contacts. Here's our coil. Here's our flyback diode. And this is the relay drive transistor. Now, just a little aside here, they have what's known as a Darlington configuration here, where we have these two transistors. The emitter of this one feeds the base of this one, and Darlingtons are known for having tremendous amounts of current gain. They actually fabricate these in a single package, but it's not unusual at all to see these composed of two discrete transistors. And in fact, virtually every output stage you see will have a configuration like this, because this would be the driver and this would be one of the outputs. And you may have heard the term dual Darlington output, triple Darlington output. That's what they're referring to. And this is what a Darlington transistor looks like. Now I'm going to invert and flip the picture so the orientation of it matches this, and you can see that that is exactly what this is. So that's our relay drive, this Darlington configuration here. Our startup delay is going to be here. It's going to be 220 microfarad and 33K. So that's going to charge up. When it charges up, it'll forward bias this transistor, which forward biases this transistor, which pulls in our relay. These are 828 and 827 are both 5.6K. These are our isolation resistors coming from the outputs. You can see they just tap right off the outputs here. Because remember, the whole purpose of this is to go between the outputs and the speaker terminals. So these are going to go to your speaker terminals. This comes in here. If we get any voltage here, it's going to forward bias this transistor, and it's going to kill our bias here and open the relay up. So they all tend to work in the same fashion. And the reason I bring this up is because it's not uncommon to have the protection circuit malfunction. Your amplifier may be fine and the problem's in your protection circuit. Or the amplifier has a problem and the protection circuit is doing its job. So it's important for us to know what its job is and how it does it. Okay, so we've got an amplifier on the bench. It's in protection. We don't know why. The first thing I usually do is I try to figure out if there's a problem in one of the amplifier stages, because that's generally what causes an amplifier to be stuck in protection. And the easiest way to do that is to read through the manual and find out where the bias test points are. Once you locate those, you can test between either of the bias test points and ground. And this will tell you if you have excessive DC voltage, because remember, your relay is going to be open. You're not going to find this at the speaker terminals. So once you find that, it's pretty easy to do. Alternatively, if the relay contacts are available, you can certainly check those. If they're not, if the emitter resistors are visible, you can always check from one end of those to ground with your meter. The bias test points are going to go across your emitter resistors. So there should be a test point. This may be one here. let's see, this is probably the other one here. If you test between either one of those and ground, that will tell you. And you have to do both channels. Remember, this is a schematic representation of only one channel in the amplifier. And if you get excessive DC voltage either here or here with your meter, one terminal grounded, probing with the other one, you shouldn't have more than a few millivolts here. If you have volts or many volts, you generally have a shorted output transistor, and those can cascade back, because in this particular amplifier's case, this is what I recommend people do. I read this on Audio Forum and it makes a lot of sense. Find out which components are bad and mark them and start tracing back from there. The damage on this one went pretty far back, and if you see this kind of damage, it's a real good idea to check the fuses in the unit, because it's not unusual at all for people to put larger value fuses in something if the fuse is blowing, and every time you do that you may cause more damage. Or worse yet, they'll just wrap the fuse in aluminum foil, which I believe is what I found in here. Or they'll put in something that's not even a fuse. I've seen screwdriver bits of the right size that were put in fuse sockets, and I think I mentioned somebody told me they found a 22 shell. That's just crazy. But anyway, if you print them out, you can go through them and you can find where your trouble stops. And this made it all the way almost back to the long-tailed or differential pair in the front end. They don't normally go that far, but again, with a fuse wrapped in aluminum foil, all bets are off and the thing could just go up in smoke. Now, not all direct coupled amplifiers have protection circuits. The vast majority do, but some don't. Many of the ADCOM power amps have no protection circuit, and some people are leery of them for that very reason, because there's a possibility if that thing lets go, it'll eat your speakers. And I have kind of a funny story from my checkered past. I was playing in a band, and we had a Crown DC 300, they happened to belong to me, that was powering the PA. And it lost the channel. Now we're playing, I can't really hear it because it's the mains, the PA, and we're listening to the monitor, so I don't really hear anything different. But this patron is coming up to me, we're playing, it's rock and roll, it's loud, he's yelling, I can't really hear what he says, but I just hear on fire, and I thought, wow, he must say, you know, the band's on fire, we're having a great night. We were having a pretty good night. Finally got the message that what he was trying to tell me is, your speaker's on fire. And sure enough, I looked over and you could see the voice coil was glowing cherry red. There's smoke coming. The cone's just about to catch fire. I just grabbed the nearest drink someone left on the table and threw it in. That amplifier had no protection. That's what can happen. That's what these protection circuits are all about. So I'm going to have a series of links with this video to other videos I have done where I have found either problems in an output stage or problems in a protection circuit, and how to troubleshoot that particular amplifier. They're all going to be a little different, but they're all going to basically be the same. You're either going to have a problem in your protection circuit, as we went over here, or you have a problem in your output stage. Generally speaking, it's going to be one or the other. Just like in most stereo amplifiers, it's usually one channel or the other. You may find occasionally, rarely, that you'll have multiple troubles like that, both channels out, protect circuit out. Or you may find that nothing works right because your problem is actually in the power supply and you got to go back there to find it. There are a lot of different scenarios that can happen, but once you get a little knowledge under your belt and you look at these things, and this works for me, maybe it'll work for you as well. I tend to think in a block diagram. Protection circuit, these are your blocks. Relay drive, startup delay, voltage detector. I think the same way when I look at this, I think the same way when I look at the tuner circuit. I break it down into its individual blocks. So anyhow, that's where I'm going to leave this video off. I hope you learned something from this, and like I said, I'm going to have some links here so you can take a look at other videos I've done and see what steps I took to find the problem. And as always, I thank you all for watching, and I like giving back to the community that has given me so much. Thanks a lot, folks.